Thank you all for coming back after lunch. I hope I'm not either too loud or don't put you to sleep. So, I want to continue with the examples that I left off with at the end of lecture 1. I still feel like I'm echoing. Am I still? Okay. I'm going to change a few things. I'm going to talk about kinematic data that's augmented with what I call feature data. Because basically this is classification attributes of various sorts. The other thing I was going to show, but I didn't because I added the movie, is this first moment approximation, so I'll jump through that. I'll talk about certain topics associated with regularization and the Cramer-Rao bound. Then I'm going to switch to the multi-sensor version. The multi-sensor with the tomographic emphasis is SPECT, that's the single photon emission computed tomography. In SPECT, you will not find a positron because there aren't any, at least not those that have not annihilated. But it is basically a multi-sensor approach to the problem that will have uses in the multi-sensor case. In that case, the operative algorithm is really Miller, Snyder, and Miller, same Snyder as in PET. And then talk about the multi-sensor version of it and some concluding remarks. To just begin, I am going to, for those who have an interest in particle filters, when we were in Lancaster, someone asked a question about particle filters, and it showed that this individual didn't really understand how they work. So I added a slide, actually, because I figured there must be at least one person here who doesn't know them and would like a little bit of a pointer to it and would not ask me. So if there's one person who asked, I figured there's a fair number more. So I will talk a little bit about particle filters, but not a lot. So here we have feature data. I'm talking about two hypotheses about the data point. The data point either corresponds to clutter. I'm thinking of a kinematic data point. It doesn't have to be kinematic, but that measurement is Z. It either corresponds to clutter, which is hypothesis 0, or it corresponds to a real target, which is hypothesis 1. All targets have the same distribution under the H1, that is the feature vector will. So the augmented measurement then, when you have a radar return,
Your hand folks. Roy, if you stay behind the podium, I don't think you need the microphone.
So it's feedback from these?
Yeah, you don't need the microphone on your body.
Well, I don't want to get yelled at. I'll stay away from the mic. I'll push these back a little bit. So I feel a little bit better like this. Okay. So I'm going to augment the kinematic measurement Z, which does not have to be a kinematic measurement, whatever measurement you have, with a feature vector. It could be a real number, it could be a vector, it could be a picture, it could be whatever. But basically, kinematic measurements are often taken from sensors that actually produce more like an image, and they're peak extractors. That peak is called Z, but there's other information that sorry. There's other information that is weird.
Keep your hands off
I can't do that. There's some drop of Italian in me, but I can't do that.
We'll give you 5 more minutes.
Okay. So this feature vector is information that's in the peak extraction process that actually is not represented by the peak. And we presume to know what that is. We'll call that feature vector U. I needed some kind of name for it. There is no good name for it. And then if you use Bayes' theorem, then the joint measurement, the compound measurement, is Z and U, and not just Z. Everything I've shown you and talked about at the moment includes Z, but there's no reason not to have U. So if you want to include it, then you will use Bayes' theorem, P of Z and U given X, and the hypothesis that it actually does belong to a real target. Then Bayes' theorem enables you to write as P of U given Z and X times P of Z given X. Notice the P of Z given X is the same distribution as we had before for P of Z given X. It's the same one. So there's one new distribution here, and that's the feature dependence on the measurement and X. Typically, the dependence on Z is forgotten, overlooked, neglected, but it's there. We can put it in. It's no harm to do so. If the data Z and U actually did come from clutter, which is H0, then under H0, X is really this auxiliary state, phi, the target absent. So it's P of Z, U given Z and phi, times P of Z given phi. So we know P of Z given phi, so there's really just one new distribution required. In any event, we're going to assume that we have all four of these PDFs are known. Two we already have, or we wouldn't be working the problem this way, and two new ones that have to do with feature vector. These feature vectors, I'm going to call fantasy feature vectors. I don't know quite how that name came up, but we needed not to talk about real feature vectors because it's usually sensor-specific, and people don't like you talking about sensor-specific features. I understand and appreciate it. So we just call them fantasy features. It's a fantasy feature vector. It doesn't really matter the dimension. The way I'm going to use it, I'm going to suppose I know their PDF. If I know their PDF and stipulate it, then I don't care what they are, and I don't even have to tell you what they are. If you want to actually use these features, though, in practice, having some guru or oracle come down and tell you what the distribution is of these features, it's not going to happen. It's highly unlikely to happen. You really do have to estimate it in practice. So you have to look at data, do it on the fly. So in practice, these are not known. You have to estimate them. But if you do assume that they are known, and if you do have them available by estimation or otherwise, then how would you incorporate them into the PhD filter? Well, it's purely algebra, it turns out. There's a marked Poisson process you can talk about and various other things. But when you're done, it is the simplest thing imaginable. You write the information factor, which was the intensity function, the updated one was equal to the old one times this intensity factor, a big bracketed term. The big bracketed term is this L, and it's 1 minus PD, as before. A sum over the data, this time it's a sum over all the data, Z and U, and it's the same ratio as before. Looks a little more complicated now, but all that's changed is that I've added, see this ratio, this little ratio in the numerator and the little ratio in the denominator. All that's changed is that I've stuck those two ratios into the problem. If the distribution of the feature under the target present and under target absent is the same distribution, in other words, if we want to remove information that if we have features, then these ratios are identically 1, and we recover the previous example. So, the previous result. So this is as easy as it gets in terms of being able to add features. You use the same function structure as before, but you multiply by an additional term. That's basically it. In two places, though, so that's fine. And what's the effect then of the classification data? It has the effect of, I didn't know a good word for it, so boosting the power of the kinematic data. Now notice it will boost the power of the kinematic data, P of Z given X, if this ratio is right. If it's wrong, it could do the other. It could do the reverse. So it's not, you are playing a little bit with fire here. Make sure that the ratios that you estimate are reliable enough to be useful and not unreliable enough to harm you. So, but if you have them and if they're accurate, which actually it seems to be a reasonably straightforward to do, tedious in practice, then these things can be helpful. But again, if you don't have the features, or if you recognize that you're in a situation where these feature vectors are so unreliable that you'd be better off ignoring them, then you can just put the PDFs equal to each other, and then they disappear from the problem. This is where I deviated from my talk in Lancaster. I added this slide. There are two basic ways to implement a PhD filter. One is talked about by Peter Willett, used a lot by him, his students, and colleagues. A Gaussian sum filter is perfectly respectable. The sum does not, I don't call it a Gaussian mixture. For those who like finenesses in words, a Gaussian mixture is a Gaussian sum that integrates to 1. So it's a PDF, a probability density function. A Gaussian sum integrates to whatever you want it to integrate to. That's the distinction. So a Gaussian sum. this has been pursued by various people, Peter Willett and his colleagues, and Vo and his colleagues. The sequential Monte Carlo or particle filter method, I believe, was first done by Sidenblad in 2005, a Swedish woman who, I don't know her current name. She married and she took her husband's name, so I don't know that name, but she's still active. I just don't know what her working name is now. But the particle methods are not that old, actually, 5, 6 years old, and they were the first demonstration, really. So how do you actually use a particle method? Well, do you use just particle methods for PhD intensity filters? No, they can be used for ordinary Bayesian single target tracking filters. They can be used in lots of ways. The particle filters began basically by an insight in Cambridge, the Bayesian School of Statisticians. There was a time in statistics where to say that you were Bayesian was almost to be a shameful thing. But that has changed remarkably in the last 10 or 15 years, and the Cambridge School is the one that did it. And they had these kinds of methods that they brought to their problems. So what happens in the tracking application, particle filters were brought to tracking by Neil Gordon and his colleagues. Neil is now in Australia. He was originally in the UK when he did this. Neil and Dave Salmon. So in the tracking applications, they go to Neil and Dave. So what do you do with particles? Remember, this is not meant to be anything like exhaustive. This is a one-page slide to tell you what they are. You distribute the particles unevenly over state space. Unevenly, well, you put the particles where there are apt to be, likely to be targets, and distribute them more rarely, less finely, in places where you don't expect targets to show up. These samples represent the posterior density. The closer they are together, the more probability or more intensity there is there, the more activity there is there. So they are, in effect, a non-homogeneous, you can see or almost hear the Poisson point process. You don't have to hear Poisson, but you hear a spatial process, and these points are parts of a spatial process. So the basic steps are you distribute them, you take particles that are distributed at time k minus 1, and you move them forward to time k to time k. It's that simple. That's all you do. All you do. How many particles are we talking about? Some people like to talk about as few as 500. They usually don't talk about such a small number anymore. I've heard numbers of 100,000. I think 50 or 60,000 is quite reasonable because I like to see definition in the distribution. I'm trying to sample definition. I like to see the resolution. I like to see its structure. If you remember the Gaussian, that Poisson process I mentioned earlier this morning with the notch in it, if you don't have enough data, you'll miss obvious features in it. So you need the samples, as many as you can get, especially when the dimension is higher. So what you do with each particle then, to update it, you take each particle in turn. You take that particle, you have a transition function, so you move it from that place and that time to another spot. If there's a random factor you add to it, the transition function is a random process. So you move it forward, you simulate that, so you add it, and there it moves forward. It's not a deterministic motion, most often. So it's stochastic. So now you move them all forward. That's your predictive density. It's just that simple. One of the advantages of doing it that way is you can put all sorts of behavioral models into it. You can make the usual almost constant velocity models and send them forward. You can say take 90% of them and send them forward, almost constant velocity. You can say, well, there are some mavericks out there are going to do maybe some acceleration, so you can put in a percentage of particles that do that. You can say, well, there could be a maneuver, so you can put in, say, 2 or 3% of the particles that are going to go off at wild angles. You can put all of these in, that's all valid. What kind of model is that? Well, still Markovian, but it's a mixture, basically. You've mixed several different kinds of motion into the model. Those behaviors that don't match what the target is actually doing will die off. That's the strategy. And those that do get reinforced, live, and replicate. I haven't talked about that yet, but I will in a minute. So each particle now is moved forward by a scheme that you can use yourself. You can choose it yourself. It's very intuitive almost.
Excuse me, is it something similar to particle swarm optimization? PSO?
I would say it's similar to, but not the same as.
There are some certain differences apparently.
I don't know what happens with the particle swarms. When the particles move forward, I'm not sure. I don't know enough about the swarms.
Yeah.
The particles move forward, but then they explore the data. I don't know how they're weighted at that point.
Yeah.
But they will feel a lot.
This is more adaptive, I guess.
This is very adaptive,
Yeah.
and I don't know how adaptive particle swarms are.
No, that's not familiar.
I think in the swarm, the particles are not independent.
Yeah.
They're not independent.
There's an assumption that it's like a group of birds flying, that they depend, the motion of one depends on.
That's right, that's right. They do have some, okay, so there's no, no. Thank you, I learned something from that. Thank you very much. I knew, I think, but I hadn't put it in this context. New slide. So, okay, so the particles move independently forward, and then they get weighted. So you now know what the location is. So you have P of Z given X. You know what the X is, you know what the Z is. So you evaluate that likelihood, and you simply multiply the weight that you had. So it moves forward with a certain weight, given to you by the transition function, and then you multiply it by the likelihood. So you have an updated weight. They don't sum to 1, but they will if you normalize it. So that weight basically is then summed up and normalized, gives you a PDF on the particles. And the problem with that approach is, if that's all you do and just continue to do it, then there's a nice theorem that I learned just not so very long ago, that no matter what these weights are, when you renormalize and resample, you will not resample about a third of them. So if you don't, I'm sorry, I got ahead of myself. I haven't talked this slide before. So you weight the particles. Now if you don't weight the particles, the weights will collapse onto a few particles. You have a lot of them, but their weights will be 0. So you have to reweight them. The way to re-rate them is not to do the weights, but to actually spatially smear them out. So you redistribute them, and that's the resampling step. And if you do that in one way, you'll wind up with multiple copies of some particles. So then you have to add a small little dither of perturbation to each to make them distinct. If you don't do that, then actually the particles collapse in the resampling step, and you wind up not resampling about a third of them, and after a period of time you'll get the same thing you had before with the weighting. You'll get down to just a handful of particles. So you must resample. The point really with that discussion is that there is an art to doing the resampling, and it is crucial to the particle filter success. And the notion that you have to resample actually is the Cambridge School of Bayesian statisticians from about 15 years ago. That's what they added that was new and different. The key things, as I understand it. They did other things too. So, if you do this carefully, when you move the particles forward from one scan to another and you resample them in a certain way, the method I like is Russian roulette and sampling. That's a detail that I can tell we probably shouldn't discuss, but it's an old method that intuitively shows you that, in fact, the particles as they move forward can be kept track of, and you wind up with not just a particle at the current point, you wind up with a whole trajectory over time, from some beginning point to the current time, and that trajectory is a sample of the posterior. And then you could use that. So that's a one-page slide on particle filters, and I can see from the question about swarms and other things that I need to make 2 slides at least out of this. So. That was to answer a question that, from Lancaster. So, why do I want particle paths? I want particle paths because I want to be able to score the path in using a sequential method. Basically, what I said this morning is that the PhD, the I filter, approximates the true multi-target posterior PDF. It is an approximation. And the key idea here with the ILRT, the integrated or intensity likelihood ratio, is to take advantage of the fact that it's an approximation. Call it a proposal density. I didn't speak of it in the particle filter, but there's a proposal density with which you choose particles. And this is a proposal density. It doesn't matter if, in fact, it's an approximation. It's okay. You know the approximation and you take advantage of it. So this gets away from the criticality of it being an approximation. So you use the I filter to approximate paths that are samples of the posterior, the joint posterior, and then you take each particle path and you score it using a sequential detector to decide if there is in fact a target along that path. The sequential detector is in fact optimum. It's an optimum sequential detector. Optimum in what sense? In order to make a decision at the stipulated type 1, type 2 error rates, it's going to require the fewest number of scans to do so, the least amount of data. That result goes back to Wall, I believe, mid-50s. So it's an optimum detector being quick as possible, and that's really good. So we can turn the proposal density, that is the eye filter, into a near optimum detector by using sequential detection for each particle path. So the procedure then is, in the first step, to generate a set of particle paths, and then score each path using a cumulative log likelihood method, which of course is recursive in this fashion. It's the old value updated to a new value, updated by, well, this is the transition function from the old point to the new point. We know the transition function, so we can score it. Then we add to it the log of the likelihood function. Well, which likelihood function is this? This is the one I talked about 2 slides back. This could be, well, in this case it is, the likelihood or information update factor from the PhD or eye filter. So that's what you add in. If it weren't this, then, and just a more standard kind of likelihood function, then that's what you would add instead. But then you would have a different justification on your hands for using the CLLR. So then you add, or concatenate really, you don't add anything, you concatenate the CLLR to the path. I call it kind of junk DNA, I don't know why, but it doesn't really, I use it to score the path, but I don't use it to affect the path. The path is not changed, the path is controlled entirely by the eye filter. The CLLR, however, is used to extract things from the eye filter output. So an example, color examples, these are illustrative only, everything is simulated. In this case, measurements are from a region that's 75 kilometer square region that, and this will imitate something like a multistatic sonar problem. Errors are, measurement errors are 1 kilometer square, that is sigma in each x and y. They're IID, Gaussian distributed. The feature vector, when it's present, will have a distribution whose mean is 3 and a variance of 1. If it belongs to a target, and it'll have a mean of 0 and a variance of 1 if it belongs to a target. So if it doesn't, it belongs to clutter. So in other words, the target shifts some scale by 3 sigma. 3 sigma is not very much separation, because if they're equally weighted, then where do they overlap at? 1.5 sigma. That is not very good PD, PFF. It's not bad. It's not horrible. And the fact that we get to use it at all, and it works well, reasonably well here, is because we are using a Bayesian method to integrate it out. That's why it accumulates and is valuable. Otherwise, on a single scan basis, you would not want to have 2 distributions separated by 3 sigma. The clutter is a Poisson point process with a mean number of either 10 or 20. Our target speeds are 8 knots, typical of the kind of thing that would be used in multistatic sonar. And also not untypical of sonar problems are problems like this. I don't know if they relate to the kinds of problems you wind up with in ionospheric research, but PD of 0.1 or 0.2 is, in radar language, horrible. Not good. That means if PD is 0.1, it means that you only get a chance to see the target every 10 times, on average, once every 10 times you actually get energy off the guy. As Oliver Drummond once said, everybody in radar feels sorry for everyone who has to work in sonar. And this is why right there. So, other parameters of interest. Again, this is not meant to be an expose about these methods, just to get your attention and hope that you will encourage you to investigate it on your own. There are many details, too many to be spoken of. A lot of them are tedious to listen to. Once you're involved with them, you'll love them and find other people don't care as much as you do because they're not working the problem. So here we have 30,000 particles. I want to keep 30,000 particles, moving 30,000 forward. Now, I'm going to add, I didn't mean, by the way, I'm always going to keep 30,000 in between. There's a nice little trick here that my colleague Brian Osborne, who ran these examples, did. He moved, basically, you see the total weight of 0.2 here. In effect, he's saying the 30,000 particles, 98% of them will move forward according to the motion model. 2% of them are going to be used for cardiac birth. 2% of 30,000 is not 10,000 now, is it? So what he does, he uses a version of what is called the auxiliary filter. He births 10,000 particles, maybe less. They're actually independent, it's not. So he bursts 10,000 particles, but he assigns a total aggregate weight of 2% to all of them. And those that don't land well will die rather quickly, very quickly. And the resampling step, which I mentioned, will bring the total count back down to 30,000 immediately. So it has this intermediate puff. It puffs out a lot of spores, so to speak, and then brings it back down to 30,000, staying at 30,000. One of the things here, someone in my earshot complained about how much storage this took, and I'll put this comment in. Maybe I should be a little bit less heavy-handed about it. But I think the memory requirements are not grave. They're not serious at all. In fact, I think they're actually minimal. What do you have in a problem like this? It's a two-dimensional problem. We have velocity. I think we have velocity in this too, but still. No, actually we didn't. Sorry, in this problem we didn't. So we have two coordinates. If we had four, it wouldn't matter. We have the PhD weight, the I filter weight, the CLLR, etc. per particle. And if you add up all of the data and assume there's 1,000 frames of it, you have about 600 megabytes of data. That's actually what we looked at and found in our files. And that would seem like a lot, but I think 24 gigabytes costs $300 in the U.S. now. In 2 years, that'll probably cost $30. Pretty soon it'll be about the cost of a button. So in other words, it's not expensive and it's only going to get better, and the speed is going to get faster as well. So this is not serious. So you can easily use 30,000 particles anywhere really. So at reasonable cost. And if you're solving a real problem, you really should just bite the bullet and buy this kind of equipment. If you're not real, if your sponsor is not real, then I would suggest you find another sponsor. So, tracks. I say they are colored patriotically. That depends on which country you're in, I just realized. And so in my case, I was thinking of France and the U.S. I will change that word in future. So red, white, and blue, the idea was that I wanted to display the CLLR as it accumulated along the paths, as the paths move forward. So I say here that the CLLR turns red, the path turns red at the end, when the CLLR is above 20, then it turns white, and then it turns blue when it's a little bit further back. Well, that's not exactly true. As the path moves forward, my threshold of 20 keeps getting bigger. And so basically, I'm only displaying these colors at the current time, so you get a sense of where things are going. The more important part here to the coloration is how do we represent 30,000 particles when, in fact, we can't put 30,000 particles on the screen? And the answer is, again, Brian Osborne's nice little trick. He just randomly selects 10% of them, 3,000. He can display 3,000. So whenever you ask for, whenever you query the screen, you take 3% of them, 10% of them, 3,000, and display them. The next scan, you take a different set of 10%. So if you have a strong track and lots of particles, then the stronger tracks, the strongest will always be visible. There won't be any problem. You'll always see them. The weaker ones, the ones that are marginal, they may flicker a little bit, like you get a flash of light, you see the retinas in the back of your brain. They'll flicker like that, you won't see them. You'll say, oh, there was a track over there, where did it go in the next scan? Well, it just got unlucky, it wasn't in the 10% that got rendered. You have to do something with this many particles, or you won't see the whole structure. You've got to review it all. And this is a way to review it all. So here is a simple example. An easy multi-static problem. There's two targets clearly visible here. Is there any way to turn off some of the lights? This will get prettier. Let me see what people do. Yeah, it will be prettier if we can turn off some lights. Is that better? Okay. This is with the features off, so there's no features at all, just pure kinematic measurements. And the average number of clutter is 10 per scan, and a PD of whopping 0.2, big. So this is what I call the easy one. complicated ones. You can see why I call it patriotic, I guess. And you can also see that it's not without its problems. This lost track here. These are basically constantly maneuvering targets because they're counter-rotating. This is track off on one. It's doing pretty well, but you can see the blue represents where the cumulative likelihood structure is large at the current time, and then it goes to white. You can actually see a little yellow in there. Use a color shading scheme. And the track history is maintained all the way back to basically points here. And you can see these are particle paths, and these are 10% represented. Up here, you see a little streak. Is it your imagination or is it real? Well, apparently it didn't integrate up. It's gone. You'll see this reacquired this target, and now it's got some hesitation here with these, but it's still basically found that target. Notice I haven't automatically extracted any targets. I'm just showing you the particles. What has to be done is to extract the paths themselves. This is a little more interesting, I suppose. Trying to pick some spot. Now this one is more interesting because you see it has got the target track, but what would you do with these little bells? So yeah, even though I brag that this is an easy problem, it's not all that easy to automate. Care needs to be exercised. There's certainly a false track here. It comes off of this one. We have a maneuver model in here, so it comes out and it's getting in here. There's some tracks here that look like they want to spawn off, but then our PD is 0.2, so. Kind of pretty to watch, I suppose. Here is fantasy features on. Still PD is 0.2. Still an average number of 10 per scan. Let me go a little further. See, this time it did not lose target track on that one. It has a little trouble, but it did find it. It's doing well on that. There's fewer spurious, noisy tracks around. They do exist right here, and there's odd little things down in here. And there's a little one that flashes up in here occasionally. So the problem is that you have data. Oh, I didn't mean to do that. You have data. This is the comparison. The easy is on the no features on the left and features on the right. The problem is you have data. It's not very good data, even in this quote easy problem. And there are lots of possibilities, lots of ways in which targets could account for this data. And the issue, the challenge, is to figure out which ones are the more likely, and that's what makes the problem hard in this case. But you can see with the features on, it's definitely better. There's less speciation on this target on the right than there was over here. Although it doesn't look dramatically better, it was not that bad in the first place. But it definitely is better. The features have calmed it down. Some of these things also, I believe, are artifacts of the tomographic imaging. I spoke of that. This is a data starved problem. Nothing has been done to try to regularize the surface. So here's now a hard problem. We've got 3 targets. The features are off. PD is 0.1, so 1 in every 10 chances that the guy you see him. And I doubled the number of clutter to 20 per scan, and you will see this is going to be awful. Here, I just randomly stop it, by the way. I don't plan for it to stop. It's wherever my finger can possibly connect with the computer. Here it has no tracks at all. It has 2 false ones, one here, I'd say 5, and this one. Here's the retinal stuff. It's all over the place. There's no good answers here. Except it did. Now here it does get it. It has it once, but it's got a huge track off. Calving, as someone called it, who came from an agricultural background. This is especially nasty. It's very difficult. There's many different ways to account for the data. Some of them are tracks. I don't know what an MHT method would do with this, but I think it would basically choke. There's false stuff up in here. It's lost track on 2 of them. It's got 1 probably, but which one? Ooh, no, it's just unpleasant. Just to finish running it out, this really is a hard problem. I would call this a broken. This problem is hard enough to break this tracker. I would not want to use it. If I had nothing else, I would use it, but I wouldn't choose it. And now with the features on, still PD is 0.1, but the features are on. And we'll see that it is actually quite a bit better. Hardly perfect, but at least it does have 3 tracks. The false alarm rate is significantly reduced, but there are still alarms of various sorts. Hardly perfect, but it's only getting contacts 1 in every 10. Here's a clear example. Any reasonable person would probably think that was a target, when in fact, from the simulation, I know it is not. But to work with data that is as bad as this is remarkable. I guess what I should do, and I haven't done it, I apologize, is play the data, just the data. But I can't be sure that you're going to have a good view of just the data, that you see if you can find the tracks. When I do it, I can't see them, not on this problem. I just plain don't see them. And I know what it's supposed to look like. So here they are, side by side. The features off on the left and on the right. So if you have features, they do help the problem if they're reliable and can be integrated up. I didn't put that in an endless loop. That stopped, so it stopped. Okay, so track extraction is important, and just a little bit about it. I want to extract the targets from this data. That's a hard problem. It's a little bit easier with Gaussian mixtures, but there are still issues. You want to extract not just the number of targets, but for every target, the point estimate of the target state, as well as what is called an error covariance matrix. It is quite incorrect to speak of this as an error covariance matrix because it is not an error covariance matrix in the sense of a Kalman filter unrelated to it. You can develop a covariance matrix that's like an area of uncertainty for the contact point estimate, but that's not the same thing as an error covariance matrix. And the key idea, basically I alluded to it before, is you threshold the CLR to decide which particles are good enough to be considered targets. As I said, it's an optimum detector. But then you trace the heritage of particles, and that's what's different, and that makes this a hybrid method. You trace the particles backward in time to a point where they have a common point. You trace them to their origin. If 2 particle paths share an origin, then they belong to the same target. And it works remarkably well. So the distinct origins determine the targets. The number of targets is equal to the number of distinct origins. There are advantages to that and disadvantages, but let me just show you some of the advantages. Got that one in time. This is a single target. There are 4 pingers of big blue dots. Lots of clutter. There's 47 clutter points here. The coloring scheme is no longer quite patriotic. When I stopped this, clearly the particles were integrating up. None of them had actually crossed the threshold that we had set because there's no origin identified. Notice that this is an open-ended thing. You'll see it in just a moment. So yellow and then red. Now, when you saw the ellipses show up, that's when it extracted the point estimate, and not 1 ellipse but 2, and I'll explain that in a minute. But it also observed that in fact there's the so-called origin, and it did the clustering not by looking at any spatial partition or which points are close to which points. It did it purely by looking to see which particle paths had the common origin. That's the only thing it used. The 2 ellipses, the points are extracted by the point estimate is obtained by looking at the current particle location of point for the current time, and only for those that are above threshold. That gives you the big black ellipse. The blue ellipse is a little different. What it does, because the black ellipse includes the covariance, basically, of all the points at current time, of all the particles that belong to a common origin. The blue ellipse is a little more refined, a little more delicate, you might say. It goes back about 20 scans or so and looks at only at the particles that were above threshold then, and only then, and brings them forward. And so it's a covariance matrix that accounts just for the most recent history. And that gives you a better estimate of what the actual covariance matrix is. What is the actual? What is the true? It's not clear. It's not clear what that would be. There's no easy way to assess it. All I can do at the moment is say, well, by eye, I clearly prefer the blue ellipse over the black. The blue ellipse more reasonably captures what I have in mind for the problem. That's not a very good answer, and I'm very well aware of it. However, the heritage method is only about 6 months old, so just to play that out to the end. Notice we don't have linear velocity model in this. It just sort of wanders around. We were thinking of something that was drifting and didn't want to put velocity into the model, just so we could show how flexible it was. It did very well with only one target and 47 color points per scan. This is 3. The one you just saw is going to be on the right. Features are on. Middling difficulty, middling help, less difficult, but some. In the middle, and no features at all on the left-hand side, and you'll see that with no features at all, this problem is essentially unsolvable. It doesn't do a very good job at all. If you set the threshold sufficiently low, you would catch it sometimes here on the left with no features. You'd also catch a lot of false alarms. So the one in the middle is more helpful, but any clue, basically the message of this slide is any clue that you have that would help you understand what is clear and what is not, you should use. 2 deficits to it. Cluster sharing is one. You have 2 targets, and here are 2 targets. This is not a movie. Were ever close in time, and they were here, then there are issues with particle tracking, where you get track seduction. A track will be seduced onto another track. That happens in the particle sense. So in this case, the red track loses some of its particle paths, and they go. I keep saying this wrong every time I say it. The green track has some particles that, when they got close, were seduced onto what I might call the red track. So there are some green-colored tracks. You can't see them, but they're there in here. So when we go to try to find the covariance matrix for all paths that belong to the green that are above threshold, some of them are over here, and that causes this huge error covariance matrix. The black, the smaller one, is actually much more reasonable because we only track back and take those things that are above threshold within the last 20 scans, and this clearly ameliorates a lot of the issues of track-off and seduction. You could wait just a little bit, and you can see that it will solve itself as it did here. It does resolve itself just simply by waiting, because these green tracks that were over in the red have gotten less powerful and have integrated out and have disappeared. So, the other one, it's a deficit and an asset. I call it egg laying because it came near a certain time with Easter bunnies and kids who, like, I have a new granddaughter, my first, and we were talking about it. And what do we do with Easter eggs? And, well, I saw this, actually, about the same time. When the target maneuvers, which it often will, well, occasionally will, it's important to know when it maneuvers. If you can estimate the maneuver time, you should. Well, with a particle filter, the particles some will not survive the maneuver, and some some burst particles will come and find the target and catch it at that point. So what happens with this method, and I don't have an example for you, is that the target will say zigzag across your display, and it will drop an origin at each maneuver, effectively identifying the maneuver time for you. So I call them Easter eggs, because it made sense to me. It looked like it too, like hidden in the green graph of the display. So that's actually an advantage. So it never occurred to me when we proposed doing this that this kind of method could actually be a maneuver detector, but it is. I don't know how good it is yet, but it could do that. If you want to hear more about it, you can come to Fusion in Chicago. All are welcome. and also to the Sensor Data Fusion meeting in Berlin in October, where we will discuss more about it. Now, this comes back to the section that I said I was basically going to skip, and so I shall, or you can read very quickly. It will be in your notes so you can read them, so it's not like you're going to lose thing. This is a more traditional approach, the more usual approach to the filter. It's not all that easy. The mean field approximation for people who like machine learning. Any machine learning people here? The mean field, I thought I saw a smile. The mean field approximation is used in some parts of machine learning, and it's actually underneath this as well. So that's meant to show how it relates. How to speak honesty is my way to explain a certain approach to the filter. Again, not important. I will point out that what a favor I've done for you, especially after lunch, this is the kind of thing I could talk a lot about. See it, the sum to infinity and an n-fold integral and this stuff. Oh yeah, so much fun. Actually, it is fun. If you like this kind of manipulation, it's quite challenging. However, regularization, this is my one slide about that, really. PET imaging, for example, is a stochastic inverse problem. Somebody actually asked me why it was stochastic, and the answer was because the data is noisy. Okay? And it happens that the Shep-Vardy algorithm, if you don't protect it in some fashion, actually make the artifacts grow worse as you iterate. They do stop, they do converge, but they get worse. So it's necessary to regularize the PET image because they know what the brain looks like, and you're not iterating to nothing, you're iterating to a structure that you have some knowledge of. In essence, the need for regularization in PET certainly is no surprise. I mentioned it earlier, the amount of data you get is finite, and you want high resolution, especially with a PET image. You want high resolution when you've got targets on a big display and you're searching for them. So you're really going to have trouble when you're estimating an intensity function from a small amount of data. Again, this is a data starved problem. Both PET's less starved than tracking, and yet they're the same algorithms. Regularization methods for PET, the one I like to talk most about is this Markov random field, but I won't talk about it today. One that's really rather clever is this Grenander's method of sieves. You can find it in Snyder-Miller's book, but it is a proper interpretation of the following loose statement, which is not going to be correct. If I take the image that the Shep-Vardy algorithm computes and then pass it through a low-pass filter to get rid of the oscillations in it, then that's the image that's more like what you want. Now that would be passing the image after you've estimated it through the low-pass filter. That's the wrong way to do it and not the right place to do it. You can take the concept of low-pass filtering and bring it inside the algorithm, and if you do that, and this language is supposed to support that thought, then you can actually build that into the problem and do it right. And so the answer you will get will be already smooth, because there are no big, large, huge variations in the metabolic rate of cells, so you know that. Cramer-Rao bounds. Oh, you can get Cramer-Rao bounds. If I'm talking about Cramer-Rao bounds for really complicated mixtures, it's usually problems, and the cost-on-point process is really a sophisticated mathematical tool when you write it down. It looks like there's no way on earth that you could possibly get a Cramer-Rao bound for the intensity function, but actually you can. First, you assume the intensity function is parameterized by some number, theta, numbers, and you want to have seek an unbiased estimator of it. I don't have to tell you what the estimator is. You don't have to know it. You can compute this without knowing the estimator. And this is the Fisher information. The inverse of this Fisher information is the Cramer-Rao bound. Now what's remarkable here is this expectation. If you remember, I paused just a few slides ago and said, see what I saved you from, this infinite number of integrals, an n-fold sum of integrals. Ooh, nasty little stuff. That is what that expectation is. It is ugly. It's intimidating, even for people who are ready for it. And the truth is, when I first saw this, I thought there was no way on earth you could possibly compute this expectation. And yet, there is the answer. Very compact answer. It's there. You just take the gradient of the intensity function with respect to the parameters. This is a very standard sort of thing with Cramer-Rao computations. Divide by the intensity function. You evaluate this at the truth. That's true. And then you integrate it over the region of interest, and that's the Cramer-Rao bound. That's rather interesting, because if the intensity function was a sum of its Gaussian sum, I actually can compute these Kramer-Rao bounds for the means, the mixing proportions, and so forth for Gaussian mixtures, Gaussian sums rather, explicitly, easily, and in a straightforward way. If it was a Gaussian mixture, PDF, and I ask the same question, I cannot do it. I don't have an explicit answer. The fact that it's normalized in one case makes it very hard. The fact that it's not normalized sum to one makes it easy. Why is that? It has to do with being Poisson. So Poisson finesses a lot of things. Let's see. So I don't want to go through more of that than that. So what is the Kramer-Rao bound for imaging, for PET imaging? Well, just to recover things, this mu is the image that you actually observe, and you're looking for your ability to estimate these lambdas. The lambdas put into a vector of image form, that's the image, that's the picture you're after. And to go all the way through, here is the Fisher information. It's an integral of these terms. Well, these terms are all knowable, but the key thing here is, yes, you can compute this. The key thing is this K. K is the number of pixels in your image. If you have 2,000 pixels in your image, which might not be too bad, it's not actually all that awful or high, this is a 2,000 by 2,000 matrix, and so you get an absolutely phenomenal size matrix, and now you want the inverse of it. Yeah, that happens every day, right? So you don't do that. So, but you're still interested, and this is where Alfred Hero, who actually is one of my theoretical heroes. I hardly know the man, but I know his papers. He's often been there. He studied this problem in the image setting in 92 and 94. He said, well, you can pick a sub-region of your picture and say, I mean, he's imagining, I suppose, that this is a region where there's a tumor. And the doctor may want to know how well defined are the edges of the tumor. That informs a surgical decision. So if it's poorly defined, well, he may order another test. She may order another test, excuse me. And but you'd like to know, is it good? Is it bad? So you can compute the Kramer-Rao bound for just that subset in an efficient amount of time. You can do that. So that's wonderful. Now, what would be the analog here of a tumor in a multi-target tracking problem? It's lovely. A tumor is a target. So you're in the vicinity of a target. You want to know how well are you estimating the intensity in the vicinity of a target? And just think of that as a tumor, and you'll be happy. And you'll be able to go and use Hero to produce the answer. I have not tried to do that, by the way. I'd love it if somebody did. But I just love the analogy that a tumor and a target are the same damn thing. Comparisons to single target. This is a comparison that is really long overdue. Larry Stone, a man I work with, he consulted with me when we put this slide together for his talk, actually. But this is the LRT. This is a well-known method for Bayesian tracking of a single target where you assume there's just at most one target, nonlinear motion, nonlinear measurement, but multiple measurements. And this is the likelihood ratio. Probability of target present divided by probability of target absent. He uses the phi state that I like so much, and Kopak did. And that's the form of the answer. That no one contends that this is inaccurate in any way. This is not an approximation. This is correct. Provably, demonstrably correct, assuming you know all the models. No one contests it, and that I know of, anywhere. This is irrefutable. Okay, well, now the eye filter. Notice the eye filter form. Everything here looks very similar. The likelihood ratio gets replaced with an intensity. True. The intensity is a rate per unit state space, and this is a likelihood ratio, and there's a kind of a rate phenomenon there, but it doesn't have to be the same. Just look at the structural form. This lambda times WW is a PDF in this formulation, and lambda times it is actually a Poisson point process for the measurements. So here it is again, except that we've estimated the clutter as process in the eye filter. And we have this new term. This is a correction term for the presence of other targets, because there might be more than one target present. There were no allowances here in this one. Here, in the first one, in the LRDT, here we allow for the presence of other targets. That adds a correction term, and you can see the similarity here. Now, if you want to drop down to the PhD, you take the estimated clutter intensity and replace it by a known clutter intensity, and bingo, this stays the same. So the connections here are dramatic. These are very, very, very similar things. But notice the work we had to do to go from the one at the top, which is fairly straightforward calculation, which would bore most people after about 5 minutes, and it'd be done though. Both of these took a lot of work to get to justify adding the correction term. For the engineers in the audience, for the computer scientists in the audience, you don't need to work that hard. You don't. All you want to know is that there is a theory here, that this is the answer, and you can use it. That is, in the end, what you need. And I would suggest you learn more about what's behind it, but you can do this without knowing any of the theory. So, on to spec, back to medical. There's something that's going to come from it at the end, if Matthias will give me the time to have it run over. A spec is low resolution compared to PET. It actually goes back to the 1960s, believe it or not. I was shocked. I hadn't really heard of the procedure until I learned PET and then learned this. Spec also costs only $500, which is wonderful if you can get away with it. PET is a heck of a lot more expensive. Probably even more expensive now. $1 per particle, right? No, not really. So it's much more widely used than PET, and in fact, PET's a very serious medical thing. If you don't really want to hear that your friend or family is going to have a PET scan. Whether it turns out well or ill, it means they're looking for something not good. So the spec, in a technical sense, is inherently a three-dimensional thing. You build up the image of the brain, say, if that's what you're imaging with spec. It's hard, usually. You don't build it up like a stack of two-dimensional cards. You go directly from a set of two-dimensional images to a three-dimensional volume. So there's observability issues, of course, with each two-dimensional image. How does this work? Well, you give a radioisotope to the patient. In fact, if you're imaging lungs, they give it to you in a gas. You breathe it in. But one way or the other, they administer it, different radioisotopes for different parts of the body, which is really rather interesting development. These radioisotopes decay into gamma photons of a known energy. You then take a two-dimensional snapshot with a gamma camera, sometimes called an Anger camera, but I guess that's too ambiguous for some people, so they call it a gamma camera now. My cardiologist, when I asked him if he knew about gamma cameras, an Anger camera, he said, "What's that?" It's gamma camera. Okay. So what they do is they move it, they position it in front of your body, take a snapshot, then move it 3 degrees, take another snapshot, and so forth, and go around the body. Whoops, wrong direction, still wrong direction. So so from these two-dimensional snapshots, that's how they fix it. And it really is a two-dimensional snapshot. Here is my heart. And it's saturated with radioisotope. Each of these are meant to be a photon generation. They go off in all kinds of directions. They go off in any direction. There's no longer any collimation effect natural from the two photons that go. So they go anywhere, a small fraction, which go in the direction of the camera. It's not as close as this suggests. Many of them do not get past this collimating lens, not a lens, but a collimator. Those that do hit this crystal, which is about a centimeter thick, they like it to be as thin as possible, but the thinner it is, the fewer scintillations there are. So it's an interesting engineering problem. I keep stressing the engineering. You can tell, I like the math, but the engineering is very, very respectable, and all of these things. And if you're engineers, you need to appreciate that it's really appreciated by others. So here we have this, they scintillate, you get a cascade then of more photons. They go into this photomultiplier tube. Notice I tried to indicate that some of these cross the boundaries of the photomultiplier tubes. The photomultiplier tubes are about that size. Different kinds of boundaries. What's that, 10 centimeters? How many centimeters is that? 5? Yeah, about 5. So they cross different boundaries, so they come out the other end, and so you have a position logic circuitry. If anyone who's worked with a complicated sensor sees these kinds of things, they're named by totally different things than more complex sensors that we use, but they are all there. And this is where I was speaking that they move the camera every 3 degrees around your body, take literally a two-dimensional snapshot. We need 3 functions here. One I'm going to call the sensor measurement model. That is the probability that you get an event detected in a location Y and a camera at location, angular location theta from you. So basically that's just a PDF of, if it really decayed at X and it is detected in camera at angle theta, then what's the PDF that if it really happened with that pair, then in fact you recorded at Y. This is the engineering. It's very careful study. You've got to write that function down well. The models will depend on it depends on the quality of the sensor. If you have a horrible sensor and it doesn't do a very good job of isolating point sources, then you're not going to do very well. But that information, the quality of the sensor, is buried in this thing, and it's an image restoration problem. It's often called a blurring function. You're supposed to know the blurring function. If you don't know the blurring function, you can't do the deconvolution to recover the image that you're after. Another function that you need is this environmental propagation model. So just because a gamma photon starts in a certain location and moves off towards the camera in a particular location does not mean it gets there. There's propagation loss function, so that's what this is meant to be. So there's actually a transmission propagation loss function in this thing. I only associated this kind of probability, until I read this for spec, I only associated this kind of thinking with more like DoD problems, where you're talking about large issues that require understanding the propagation path. And here it is in my doctor's office. Okay, well that's good. That was actually very good to know. These problems run all throughout any sophisticated application. It depends on the camera geometry. It also depends on the attenuation. That means it also depends on the tissue it's trying to image. So there's a little bit of incestuousness here. So you've got to be careful about it and calibrate this thing well. Then there's a function I don't know a name for. I want to call it the sensor opportunity function. So if there's a decay at X, what's the probability it runs off toward camera J? Well, that depends on how close, for example, the camera is. If it's a camera that's over by that door, then it's less likely to go over there just because its aperture is small. If the camera is close to me, it's going to be bigger. If it's the same camera but it's on some kind of moving arm, then of course I have to adjust for that. And that's what this P of theta does. I have to know that function. I have to know all three of these. And to know all three of these well means that I have to be a really good engineer. EM. Oh, EM again. Okay, well, I'm sure we all want to see that after lunch, so I'm going to give it all the attention it deserves and go right on to the answer. The marvelous thing about the previous slide, if you read it later, is that there's an E step and an M step, which is maximizing a Q function. This is the only problem that I know in the entire literature. Maybe there's another, I don't know. See, that's the whole point. Where doing the maximization step requires solving a calculus of variations problem. All the other problems I know are algebraic in some fashion. This is not an algebraic maximization problem. I think that's just wonderful. But that doesn't mean everybody else is thrilled. Here is the answer, though. It's an iterative problem, just like with PET. You have the intensity that I'm after. This is now a three-dimensional intensity. This would be, for spec, it would be the three-dimensional, it represents the three-dimensional volume, say, of my chest. It's the current version of it, the new version of it, and it multiplies a sum. It's a sum over all the cameras of this. This is the opportunity, camera opportunity probability that I said you must know. And then notice this big term in brackets. Does anyone see a connection to the PhD filter? It's exactly what it is, except that here's the likelihood function of the data. There's a beta in here that's playing the role of a PD function, probability detection function. And this lambda m is in the bottom of all the terms in this sum, but it's still a sum over all the data of that camera and a common current state of what the image is. So the grand image of all the sensors gets fed back to each individual sensor filter. That's the feedback right there. And then each computes its own information update separately. You feed them back to the central site, and the central site waits and adds them. And it's done. That's what filter is. That's what makes this thing so remarkable. So how does it work? Intuitively. This is a map estimator. This is a maximum, optimum estimator of the distribution of radioisotope in the body. So how would it work? Intuitively, suppose my heart had a hole in it, so it's a perfect torus. I've got to say things like this to keep people away. There's a torus, and so it's staring straight out, right? And So if I have a camera in front, what am I going to take a picture? What's it going to see? It's going to see a ring. A ring. It's going to have a hole in it, just like she said. And I'm joking. And so you're going to see a ring, and that's all you get. Now, there's no range. Notice there's observability. Two-dimensional picture doesn't tell me where the tissue is. I know there's a min and max range, but I know that because I set the experiment up. The camera, the picture, has range limitations. It's range blind. It's very passive, like passive sonar. So it's a cylinder, really. The reconstruction 3D image from one two-dimensional slice is a cylinder. Thick cylinder, properly sculpted to account for this uniform distribution and so forth. So now let's go to the extreme, and I go to a camera off to the side. Take a similar picture. What's it going to see? Something like a little pill, roughly rectangular, rounded at the corners. That too is going to be a slab. It doesn't have range, so it's got some min and max range. So now this thing says that my optimum image is the sum, not the product. See, these are intensity functions. They do not multiply. They add. The units are wrong if you multiply. They look like PDFs, and if you multiply them like good Bayesians should, you'll be dead wrong because they're intensity functions. They're not PDFs. Sorry, that's one of my messages. So you add these things, and so what do you get? You get the sum of a cylinder and a slab. And so, of course, you have edge effects. You can see them in your brain. But where they overlap, you'll begin to see sort of a clumpy, you'll see an outline of something sort of like an annulus. It'll be poor, but that's why you take other pictures. And you add them all together, and that's the image. And that's the whole filter, and that's how it works, and it makes perfectly good sense. So, the multi-sensor case. Well, what do you think I'm going to do, folks? I'm going to take the same target model that I had before. I'm going to say it applies to the radioisotopes. It's a good model. If it was a good model for PET, you bought it for the single sensor problem, then it's the same model I'm going to use here for multi-sensor. So if I use it and assume that that is a reasonable thing to do, and it seems to me to be very reasonable, then the sensors actually become independent, not conditionally independent. Remember the coin flips, 100 on average versus 100 exactly. That difference makes all the difference in the world. The intensity functions now add. If I make the assumption that they're all equally good, then it really is truly an average. Why is it an average? There's a reason for the 1 over m. What the intensity filter, what the spec said is to add them all together. Because each one is separate. There's a reason. It's a detail. Here I divide by m the number of sensors to get the count right. And that's basically all it comes to. So in essence, the multi-sensor intensity filter forms the intensity filter for each sensor, reports it to a central fusion site, and then adds it to all the other sensors in the field. That's the optimum answer. Haven't tried that out yet, by the way, but I will be soon. Variance reduction. There is one thing I want to say about variance reduction, which is that one of the problems with the PhD filter, intensity filter, is that the mean is equal to the variance. I think I said that on like the first few slides. That's a problem. Where else do you have that problem? Any signal processors in the crowd? There must be. You want to estimate a power spectrum of a stationary signal? Well, you could take one long, huge DFT to get the maximum resolution. I know, I saw somebody shake their head. You don't do that. No, you don't. You block it into records, non-overlap records to keep it simple here. You do an FFT on each record, magnitude squared each, and then you average them together. And the Wiener-Kinchen theorem, if you want a theorem, says that average, in fact, is the power spectral estimate. So you trade, and the variance goes down. And the more you average, the smaller the variance gets. Now, when you trade it off, then what? You trade it off resolution. That's the long DFT with very fine resolution, but lots of variance, too much to even see anything, because the variance is equal to the signal level. That's nasty. It was very nasty. The periodigram was terrible to work with. But it was Bartlett who said, in 1947, a great year, said you average the periodigram. Huge advance. Of course, you couldn't do that until computers came along. You could do it well. But when you average it, you trade off the resolution for variance reduction because you're averaging. And now you get the stability, and in this less resolved world, you get a very stable power spectral estimate if your signal is truly stationary. This is doing the same thing, and that's what this slide is meant to convince you of. But again, it's after lunch, and I won't go through the algebra. It's in the slide package. But so one reason that you use multiple sensors, and Matthias points at his thought, is to get the variance down. And so in that sense, if you speak purely in the spirit of variance reduction, give me all your senses. I will take your huddled senses, straining to be free. Sorry, that's the American thing. And we will integrate them, and yeah, we'll try, and make a better process out of it. And that's what the basic thing is. Use all the sensors, use them properly, bring them all together, add them. That's the answer, and it's not a problem. That's what the theory says to do, and it's an optimum thing to do. So in conclusion, Matthias, and to the lecture series as well, it's quite an honor to be invited to give a series of lectures like this. It really is, and I thank everyone here for coming, and your institution for sponsoring us. But to finish my remarks, and not with get distracted by the thank yous, I hope I have convinced at least some of you that these new filters, they're fairly new, that they are really tomographic imaging filters, and that the image space is the target state space. It's an approximation. I say it's based on a flawed physical model of real targets. Well, that's true, because if you're trying to track planes or submarines and you tell the captain of that vessel that, oh, you're no different than a positron decay, I don't know how long you'd have your job. So it's certainly a flawed physical model, and you don't want to describe it that way. But with all the analogies in place, you can do that with your colleagues and find another way to represent it to the men and women who serve us so well. These intensity filters are linked to important signal processing problems, PET and SPEC, and at the very end I alluded to another one which is really cuts across many fields, and that's power spectral estimation. They are important in tracking as well because they give a physical model for the target that has not been reported elsewhere in the literature. You will see people talk about first moment approximations and a posterior, and it just goes on and on. And where's the target model, folks? You can't find it. It's not talked about. It's a nice mathematical abstraction that does nothing for intuition, does nothing to help understand what they are, why they're good, and why they might work in your problem. So the physical interpretation is very important. Lots of things need work, especially after you see the connections. There's the Kramer-Rao bound. I reported on the Kramer-Rao bound for a pixelated image. Notice I very carefully did not talk about a Kramer-Rao bound for a function. That concept is a mathematician's dream. I have no idea how to write that problem down properly. So I keep it pixelated to keep it finite so I can use the theory. So I wanted to point out that I did finish that one myself. There are artifacts that I think will, when they're properly corrected, will make these filters much more interesting, much more stable, and be very useful. You can also do online estimation of target berth and clutter by these intensity filters. I said before that one of Wolfgang Koch's students actually showed that the I filter outperforms the PhD filter even when the clutter is matched correctly. They're both approximations. It doesn't mean that one has to work better than the other, but it actually outperforms it even in a matched situation. So these are good things. Variance reduction from the multi-sensor averaging, I think, is actually in the long term possibly going to be the most important. If that swarm that I didn't get right before turns out to be semi-sentient, then and there's some master of the hive, then averaging over the swarm's image of the world could be a nice way to solve problems. So, conjecture, might as well end on a conjecture. Thank you very much for your time. Oh, sorry, I got to end on an ad. This is my book. I don't have the cover for it, but it did come out in 2010. It is not 1,500 pages long like Peter Wells' book. Published by Springer. I'm very proud of the fact that if you go to the American Amazon anyway and type in Poisson and Streit, you'll find my book. So it's reasonably priced, but that's not the point. If you like these kinds of things, I tried to make everything very accessible in this book. I did not use measure theory, for example, though the fact I didn't makes me want to cry at night. But it's not you don't need it. You can see a lot. You can learn a lot without it, and it's not
Just by reading.
Just by reading, and it's accessible. There are books on these processes that I cannot read. So, at any rate, That's my last, that truly is my last slide. Now, are there any questions?
Can we go now?
Yeah, I was waiting for it to see it.